Hello everyone. In this final session, let's look at the remaining part of integration for our ASET module. A lot of mechanisms of integration have been covered in the previous two sessions. But what will a few more things that are left out typically are, if at all, I'm not able to find out the integration using the traditional method, especially for a definite integral. Because my intention always of using an integration is finding out the area under a curve. So the area under a curve typically will have some kind of bounded intervals. So what if I'm not able to use the traditional integration formula method to find out the integration? That is where sometimes I may resort to the mechanism called the numerical method, which is more of an approximation mechanism. Probably it may not give me the exact value of the integral, but it can very well approximate something for me. So the way it works is, let's say some curve like this is there, right? I want to find out the area under the curve between this and this point, between some a and b. These are what is the definite integral. And now if I am not able to use any kind of a traditional formula to find the integration for this, the simple way is divide this area into small blocks of some length d. Now what is happening here? This is forming a kind of a trapezium. So take the area of this trapezium, which is nothing but half height into the sum of the two parallel sides. Sum of the two parallel sides. That is what we are calling as the area of the trapezium. So take the area of all these trapeziums and simply add them up. That is what will give you the area under the curve. That is what is the typical numerical method that is applicable in this context. So how do I do that? The simple way is, so now if you see the first part is half, let's say if I take each of them as P, Q, R, S, so my this thing becomes half D into P plus Q. And the next trapezium becomes half D into Q plus R. The next one becomes half D into R plus S. Now if I add up all these, what is coming out? Half D into P plus 2Q plus 2R plus 2S plus so on, and again the last one, whatever it is Z, that does not repeat. But rest of all in the middle they are repeating twice. So that is what we are calling as the values. Now, so here if I want to find out for the first one, so here what is the, let's say if I want to try to find out the area under the curve y equal to 2 by x between 2 and 3 using 5 ordinates. 5 ordinates means I am actually breaking my whole data into 4 parts. So probably x equal to 2, 2.5, 2.25, 2.5, 2.75 and then 3. So I need to find out the length of y for x equal to 2, x equal to 2.25, 2.5, 2.75 and 3. So that is what will be the length of my trapeziums. So what I can, the parallel sides of the trapezium. So I am trying to find out what will be the values of y when x equal to all these things. Let me try to put it in a spreadsheet. It becomes easier for me. But yeah, You have to do it using your calculators itself. Now, I have the values 2, 2.25, 2.5, 2.75 and 3. And what I am saying is equal to 2 by this number. So my y's are these things, 2 by 1, 2 by, so my x's are these and my y's are these. So for the first one, these two will be my parallel sides. So what is the area for the first part? Equal to half, a half, base in all the cases is 0.25, which is the distance between the parallel sides, into the sum of the parallel sides. This plus this. This is the sum of the two parallel sides for the first one. So the first one area is this one. Similarly, I can do the area for 4 of them. This is the areas of all the 4. And as a summation, I am getting the value 0.81. If I am doing the summation of all these 4, I am getting an area of 0.812. This is how I do the integration between. So without actually doing an integration, I am able to find out the area of the curve using the numerical method, kind of a traditional mechanism, non-traditional mechanism. Now, if I try to do the integration, because this is a very simple example, integration also exists. So, if I say between 2 and 3, 2 by x dx, just trying to see how close is our answer. So, 2 by x dx, so 1 by x is nothing but log x. So, I'll say log x, 3, 2. So, it is nothing but 2 into log 3 minus log 2. Okay, let's see what is it coming out. Log 3 minus log 2. So, equal to 2 into log 3 minus log 2. 0.8109. Whereas we have got 0.8123, more or less matching even up to 2 digits. So if I am not able to find here, just to see how well I can use even the numerical methods mechanism, especially the trapezium rule kind of a mechanism, to find out the integration, even if I don't know the typical integral value of the, even if I don't know the typical integration, I can do the integration using the trapezium rule kind of stuff. That is what is being highlighted in this, because when I do it even through the integration, I am not losing out anything big on it, right? So the trapezium rule is something which you have to be comfortable with, which is nothing but break the whole area into multiple chunks and equal size chunks, so that your d remains the same. Only the sum of the parallel sides will keep differing in all these aspects. Then the another common thing which is typically used from an expansion standpoint is the usage of the Taylor series and the Maclaurin series. So let's say if the question is about expand log x for x equal to e. So if you want to approximate some value of f of x, when x is very much approaching a, if you want to find out what is the value of f of x, when f is approximately equal to a, I can use the Taylor series of this kind of a form. So f of a plus h. Why are we doing a plus h? Because it's not exactly a, it's approximating, it's approaching a. So if I want f of a plus h, I can very well write it as f of a plus h into f dash of a plus h squared by 2 factorial into f double dash. F dash is nothing but the derivatives. So if you just want, let's say I want log x for x equal to e. So I will write it as f of e plus x minus e. This is correct. This is h. H is a very small value. F of a plus h. So how should it become? F of a. F of a is nothing but f of e. What is f here? Log x. Log e, which is 1 plus h x minus e. You don't need to remember this. These are all present as a part of your table. H into f dash of a. What is the f dash of x? Log x. What is the derivative of log x? 1 by x. 1 by x, which means 1 by e. F dash of a plus h squared by 2. H is x minus e. X minus e squared by 2 factorial into f double dash of a. What is the f dash of 1 by x? 1 by x minus 1 by x squared is the derivative of this. So minus 1 by e squared. Again, h cube x minus e whole cube by 3 factorial. What is the derivative of minus 1 by x squared? 2 by x cube. So it is becoming 2 by e cube. So that's how you expand the value of f of e, f of x when x is approaching e. So you have to remember, when someone is asking about finding out the f of x value at the point when x equal to a, which means I can very well use the Taylor series approximation to find out the value of that particular function. The Maclaurin series is a special case of the Taylor series. The only difference being, you don't find at x equal to a, you always find at x equal to 0. So it becomes very simple for us. Now if you say find log x, log 1 plus x, I don't try to find log 1 plus x at some other point. I am more bothered about trying to find out log 1 plus x as a generalized expansion at x equal to 0 itself. So what happens, I'll try to put f of 0. F of 0 means log 1 plus 0, log 1, which is 0. Now here, all I need to find out is log 1 plus x. Now I need to write it in the form of x equal to, I need to check it out for x equal to 0 itself. So in the same, if I try to substitute, if I try in the Taylor series itself, if I put a equal to 0 and h equal to x, which is nothing but, it comes out to be the same. So log 1, it is 0. So the first part is 0 for me. X into x is here log 1 plus x. So when I want to expand log 1 plus x, I'm simply putting f of 0. F of 0 is log 1. Log 1 means 0 plus f dash of x. What is f dash of x? 1 by 1 plus x. 1 by 1 plus 0, which is 1 plus x squared. 1 by 1 plus x whole square, derivative of 1 by 1 plus x minus 1 by 1 plus x whole squared. So x squared into, put x equal to 0, minus 1 by 1 plus 0 whole squared, which is 1 itself, but 2 factorial. Then similarly, f of plus x cube into, then what is the derivative of minus 1 by 1 plus x whole squared? 2 by 1 plus x whole cube into 3 factorial. So this is how you can expand this particular thing, especially if if the question does not ask about a particular point, you can very well use the Maclaurin series. If it is asking about a particular point, finding out the value of the function, then you can go for using the Taylor series itself. So when the questions are framed in this manner, you have to use these approximate series to find the values at a particular values. Then one more concept which we have to discuss in this context is the usage of the differential equations. What is a differential equation? Any equation which contains d power n y by dx power n, like okay, if something says dy by dx equal to 2x plus 3. So something like this, if I have, then we call all these kind of equations as differential equations. A derivative is present. Whatever is the order of the derivative, it may be a first order, second order, the derivative is present as a part of the equation. We call those kind of equations as differential equations. So there are three methods of solving these differential equations. Or as far as our syllabus is concerned, we focus on three different methods to solve for these differential equations. The first one being a direct integration method. So if I take the example like this, d squared r by dt squared equal to 2t squared. Now if I take the differentiation of this, right, or probably we'll take this example directly. D squared x by dt squared is equal to at squared. Now if I integrate d squared x by dt squared with respect to t, what will it become? Dx by dt, right? Because it's a reversal of differentiation. So if I integrate d squared x by dt squared with respect to t, it becomes dx by dt. Whereas this side, integration with respect to t becomes a into t cube by 3. Are you with me? Again you integrate this with respect to t, it becomes x. Again you integrate this with respect to t, it becomes t power 4 by 4. And probably for the whole thing I'll put some plus c. So finally it is working out to me as x equal to a t power 4 by 12 plus c. Now it is saying some other things. When t equal to 0, x equal to 4. So 4 equal to a t power 4 is becoming 0, c. So c is coming out as 4 in our example. When t equal to 1, x equal to 97 by 12. So all I can say is 97 by 12 is equal to a by 12 plus 4. So a by 12 is equal to 97 by 12 minus 4. 97 minus 48, 49 by 12. So a is working out to 49 here. So it is directly coming out to us that x equal to 49 t power 4 by 12 plus 4. Now when t equal to minus 1, you can try it out. Okay, here when t equal to minus 1 also, x is equal to So you can very well solve for the values of a, b, c through the integration itself. Let's say you have this equation to work out on. D squared r by dt squared is equal to 2t squared. Integrate with respect to t. This becomes a dr by dt, and this becomes 2 into t cube by 3. Again integrate it with respect to t. You will get r into t power 4 by 4. R equal to 2 by 3 into t power 4 by 4. So especially in some kind of expression, you can solve for x. Even though the expression is in the form of a differential equation, you can solve for the values of x or r or the variable by doing a plain integration. This is one form of solving the differential equation. We also have a couple of other methods to solve the differential equation. One is separating the variables. Separate the y's, separate the x's, handle their dy by dx's separately. Like this. X squared by plus 9 dy by dx is equal to xy plus 2x. Probably the right hand side first I will write it as x into y plus 2. Now I can separate all the x's. X squared plus 9 by x dy by dx is equal to y plus 2. Now I will take x's, all dy's to one side, all dx's to one side. How do I do that? I'll make it as 1 by y plus 2 dy is equal to x by x squared plus 9 dx. I can do the integration on both the sides. Applying integration on both the sides, this becomes log y plus 2 plus some c is equal to, what is the integration of this? If you see here, the f of x is in the denominator, and probably if I do a 1 by 2 and I put a 2x here, the derivative of it is there in the numerator. So I can very well write it as half log x squared plus 9 plus some k. Log y plus 2 plus c is equal to half log x squared plus 9 plus k. That is what is the relation. And it is also said that where y is greater than 0, x equal to 4, y equal to 0.5. So you can very well say when x equal to 4, so half log 25. So all constants probably will take them as one unit. Half log 25 is equal to log 2.5 plus some k. Now k is nothing but half log 25. Half log 25, using our rules, we can write it as log 25 per half, and 25 per half is nothing but 5. So log 5 minus log 2.5. Now again you can know log a minus log b is log a by b. So log 5 by 2.5 and k becomes log 2. Now you can write your expression very well. Log, so k is coming out as log 2 directly. So you can very well write it as log y plus 2 plus log 2. So which is nothing but log 2 into y plus 2 is equal to half log x squared plus 9. Log square root of x squared plus 9. Remove the log. 2 into y plus 2 is equal to square root of x squared plus 9. Now you can very well do the squaring. 4 into y plus 2 whole squared is equal to x squared plus 9. Now you can simplify it to whatever extent. This is what is the solution to that differential equation. So the main context here is, if at all I am able to separate out the two variables y and x, if they are separable, I will definitely separate them out and do their integrations separately. So all y's I will bring under dy, all x's I will bring under dx, do an integration on both the sides and solve for the inequality, solve for the equation. This is another way of solving a differential equation. The third method that is being talked about in our context, in our subject, is using an integration factor. Especially when I see a differential equation of this form, dy by dx, wherein y is also there and some f of x is here, and the outcome is given as g of x. If I have an equation of this form, we can use an integrating factor. The integrating factor is nothing but e power integral f of x dx. Now let's see this. Okay, if I take this, how do I try to write it in that form? Okay, dy by dx is equal to y squared by 3xy. How much is it? Y by 3x plus 2. What I'll do is, I will bring the y by 3x to this side. Minus y by 3x is equal to 2. Now this is more like this form. If you see here, dy by dx. So y is there. So I'll write it as f of x is minus 1 by 3x into y. So f of x into y is equal to g of x. So in this case, I can take it as an integrating factor, and the integrating factor for me is e power integral of f of x dx. E power integral of minus 1 by 3x dx. What is that now? E power minus 1 by 3, if I take out, 1 by x is log x. Right? 1 by x is log x. The integral of 1 by x is becoming log x, or probably log mod x plus c. So this is what is the integration function. Now what I'll do is, I will multiply left hand side as well as right hand side with this. E power minus 1 by 3 log x. So what is that? It is becoming e power minus 1 by 3 log x into dy by dx minus y by 3x e power minus 1 by 3 log x is equal to 2 into e power minus 1 by 3 log x. Here comes the twist. You try to see this two put together. This entire thing put together. This is nothing but dy by dx of y into e to the power of minus 1 by 3 log x. You see this? This is nothing but the derivative of this one. Derivative of this one. You just see here. Derivative of this one. You see y into e power minus 1 by 3 log x into 1 by x. E power minus 1 by 3 log x dy by dx. So this entire thing happens to be the d by dx of this. So if I don't want the d by dx, I am doing the integration of that. So integration on both the sides. Y into e power minus 1 by 3 log x is equal to 2 into, first of all, now e to the power of minus 1 by 3 log x. What is its value here? So this minus 1 by 3, first of all, I can take it to the power minus 1 by 3. E power log x is nothing but x. So this becomes directly integral of 2 into x to the power of minus 1 by 3, which is nothing but 2 into x to the power of 2 by 3 by 2 by 3, which is 3. So y into e to the power of minus 1 by 3 log x equal to x to the power of 2 by 3. And even this one I can simplify. E to the power of minus 1 by 3 log x, I can make it x to the power of minus 1 by 3. So y into x to the power of minus 1 by 3 is equal to x to the power of 2 by 3. And again I can bring it down, right? This is 3 into x to the power of 2 by 3. So I can very well bring these things down and I can simplify the process. Probably plus c is something which I can put up. So this is what is becoming as a simplification. So especially when I have an integrating factor around, I can do the solution of the differential equation using this integration factor, and probably I can substitute y equal to 1, x equal to 27, these kind of things, and I can solve. So as a part of the differential equations, as a part of this particular curriculum, we are talking of 3 different models. One is when I can do a direct integration. 2 is I can separate the variables and I can do an integration. And 3 is I can use an integrating factor, especially when I have the differential equation of the form dy by dx equal to f plus f of x into y is equal to g of x. I can very well use an integration factor to typically solve the differential equation. I hope you are comfortable with the usage of Taylor series, Maclaurin series, solving the differential equations, and also using the numerical methods. So try to integrate all the 3 parts which we have done for integration. Try practicing all the various numericals in the areas of integration. If you have any further queries regarding this, feel free to give me a call on the mobile number that I have given below, 984801212, or you can even drop me an email on Vamsidhar@pacegurus.com mentioning your doubts, and I would be very much happy to solve them. And I request you to visit my website www.pacegurus.com to get a further insight into the various trainings, consultings, and the new training videos in the areas of finance, investment, statistics, analytics, and actuarial sciences using various tools like Excel, VBA, SPSS, etc. I hope by going through this session you are definitely getting some level of insight into your practice for ASET exam. Thanks a lot for listening to this session. Thank you very much.